welcome back. So, we are going to look into the discussion and continue our analysis on the common mode feedback, where we are going to replace the present common mode feedback scheme with an active common mode feedback, where we will get rid of these two resistors in order to extract the VCM. So, let us see how can we do that. So, once again I will redraw the fully differential amplifier. And I will have a slightly modified version of our differential amplifier with current mirror load, where one of the input device has been split into two. So, if this is W, each of this is W by 2, and obviously, if you are having the gate biases almost at a similar value, you will also have the ID flowing in these two branches almost similar, and as a result ID of these two devices will also be half of ID of this one. So, if this is having ID by 2, each of these will be having ID by 4, ID by 4. As a result, what I can say is the GM of these two devices will be half of the GM of the device over here, because we know that GM is proportional to root under W and I. So, if the W of these two is half of the W of this device as well as bias current is half, of course, the GM is going to be half, each of these are going to have the GM of this one. So, let me number this 1, 2, 3, 4, 5, and let me call this 6, 7, and now the load side I will decide upon the diode connectivity once we discuss the polarity. So, let us leave that for the time being. Now, one of them will have the diode connection, because this is the current mirror load. How will be determined the diode connection? That again depends upon the negative feedback polarity. So, now if we connect the two outputs over here, say VO1 and VO2 to these inputs. So, what I am going to do ultimately, I am connecting VO1 over here and VO2 over here. So, these two outputs are brought and connected to the two input devices over here. And that condition, what can I write about the common mode or the differential current signals flowing through these two. So, if I am having the output signals over here VO and VO2, and if I assume that this is a source which is not necessarily at AC ground, because if the signals are not fully differential, it may not be exactly at AC ground. So, suppose there is some small signal Vs coming over here. This is our reference signal Vref, and I want my output common mode of the differential amplifier to be set equal to the reference signal. As a result, if I look at the small signal current combination flowing from these two transistors, let me call this 11 and 10. So, if I look at the small signal current flowing through these two transistors provided by these two pull down devices, I can sum the small signal current flowing through these two. So, I can write the ID10 is going to be equal to GM5 which is GM by 2, if I call GM of M7 as just GM. So, the GM of M5 is just GM by 2. So, ID10 is going to be GM by 2 times VO1 plus, or if I assume that the source is not at AC ground. So, I should basically take VO1 minus Vs plus another GM by 2 times VO2 minus Vs, and therefore, I can write down ID10 as GM times VO1 plus VO2 by 2, right, plus GM times Vs, or rather minus GM times Vs. So, this is the extraneous component that is coming. Likewise, on the other side, if I see this is a DC potential, this is Vref, which is a constant DC. As a result, there is no AC signal over here. So, therefore, what is the small signal current for ID 11? So, if I write the same thing for ID 11, that is going to be GM times VGS. So, VG of this is 0 because the small signal value is 0. So, VG becomes 0 minus Vs. Therefore, if I look at the differential signal, differential current, ID11 is just Gm times minus Vs minus GmVs, ID10 on the other hand minus GmVs plus this quantity. As a result, this is the common quantity which will get subtracted if you look at the differential operation. So, I do not need to worry about this. Effectively, the overall signal that is coming is equal to Gm VO1 plus VO2 by 2, which is nothing else but thus VCM. Therefore, the effective differential signal which is coming at this differential input, overall differential input is just Gm VCM. The effective VD for the error amplifier happens to be just Gm VCM. So, basically this split differential pair is extracting the VCM of the first stage. So, it is helping us in obtaining the VCM in an indirect fashion. We have got rid of that resistive divider, and with the help of this split pair we are able to extract the VCM. Now, if you look at the polarity, once again if VCM goes up means both the signals are going up, or the common mode level of the first amplifier, the main differential amplifier is going up. That means the voltage over here will be going down and this potential will be going up, and we know that the upgoing potential is to be connected to the PMOS. Therefore, this is supposed to be my output which is supposed to be connected to the PMOS gate. So, I will once again make the diode connection over here and connect the output of my error amplifier to the gate of M3 and M4. Therefore, once again if the common mode voltage of the fully differential amplifier goes up, this is the effectively the non inverting input of my error amplifier. If this common mode goes up, the output over here will go up. As a result, the PMOS gate voltages will go up, and as we discussed in the last session, it will try to bring these two levels or the common mode level over here back to the reference value, which is the Vref. So, this is once again doing the similar operation, which is we are able to establish a well defined precise Vref at the or common mode voltage at the output of the fully differential amplifier with the help of this error amplifier. Now, in general, when we go for operational amplifier design, we know that we will be needing multiple stages. We will need 2 stages in a given operational amplifier at least to get a larger gain, and the second stage is also active load and fully differential. So, how do we incorporate common mode feedback in such a case? So, we can look at that scenario where we have a fully differential op amp where you have 2 stage amplification. So, basically the output of the first stage is fed to a second stage, which is going to be simply common source amplifier. So, all these are bias points. So, this is VB, which is a fixed bias point, and your inputs are over here. I am not showing the input bias point for the main amplifier, and here in this case we have the first output, which is active load, which is not having a well defined DC point, and also the second output is also an active load, which is also not having a well defined DC point. What is the overall gain of this circuit? If I talk about the differential gain, the first stage is same as our fully differential amplifier. Therefore, the gain from V1, V2 to VO1 and VO2 over here remains same, Gm RO by 2. So, the differential gain remains same. We will assume this point to be AC ground, and then this becomes a common source amplifier with active load, and therefore, the gain expression from these 2 inputs to the output remains same. After that, basically you have just another common source stage. So, these 2 transistors are just providing you another common source stage where these 2 bottom transistors are active load. They are biased with a fixed DC potential, they are providing active load, and these 2 are the input devices or the input devices of the common mode common source transistors. Therefore, these 2 stages are also going to provide you similar gain factor Gm RO by 2. So, this is a common source amplifier, input device, the load device, and therefore, the gain from here to the output is again GMRO by 2, and these are also active loads, and therefore, we do not have a well defined DC point over here. So, now in this particular amplifier, how can we set the DC bias point for both the stages? One option is that we sense the common mode at the final output only, and then control the bias point of the PMOS transistor by the single error amplifier, assuming that it is going to set up the common mode level over here appropriately, such that the final common mode output over here is at the desired DC point. So, there is one option. I can just sense the two outputs over here and extract the common mode corresponding to these two outputs, and then generate the error signal, which is going to control the bias point of the PMOS. But a safer option would be to control these two DC points separately. That means, I would use a first error amplifier to control the DC bias point of the output of the first stage separately. So, I will say VCM of the first stage compared with Vref, and then provide the control signal VC1, and then use another one to get the VCM of the second stage, call it VCM2, and then provide, and you can, the Vref can be different, Vref2, and provide another control voltage VC2 to control the gate voltages over here. So, rather than fixing them, you apply another gate voltage VC2, which is coming from the error amplifier. So, in that case, I can control the two DC bias points for the output stage and the first stage separately and safely. So, in simulation exercises, we can see that what happens if we rely on a single error amplifier and try to control the output DC point by just adjusting the VC1 with the help of single error amplifier. That can be a more risky case, and it will be more clear when we look at the corresponding simulation example. It will be better to explain with that. So, in general, for more robust design, people prefer having separate common mode feedback for the two stages. Now, after going through this basic operation of common mode feedback, we need to look into some of the important aspects associated with this common mode feedback loop, namely stability first of all. So, whenever we are having negative feedback in the circuit, it is very important that the feedback loop is stable and we are not having unwanted oscillations which can corrupt your overall operation. Therefore, once again, the stability analysis of the feedback becomes important, and for stability analysis, we can first of all find out the feedback topology of this circuit, look at the overall high frequency poles coming in this circuit, and then look at the considerations that we can make to ensure overall stability and the feedback loop. What kind of compensation, what kind of components are supposed to be added, so that we can make sure that the overall loop is stable. So, before we go towards stability analysis, first of all we need to look at the equivalent common mode circuit, because ultimately this is a common mode feedback, and therefore, we need to look at the common mode half circuit for the original amplifier clubbed with the error amplifier to arrive at the overall common mode circuit for which we will be analyzing the stability. So, let us quickly look at the common mode half circuit for which stability will be analyzed. So, we know that for single differential amplifier stage, when we arrive at the common mode half circuit, we will be basically combining these two transistors together, combining the input devices together, assuming that the input voltage is same, because if the input applied voltage is same, the common mode value, the output DC point will be exactly same. As a result, we can tie them together. So, in the common mode half circuit, we simply tie these two nodes together, and as a result, in the equivalent common mode half circuit, I will have the two transistors M1, M2 and M3, M4 tied up together. So, I will have this as M3 plus M4, and the input device will be reduced to M1 plus M2. For the common mode, of course, we do not have this point as the AC ground. So, we will have the M5. If I call this M5, I will have the M5 also coming into picture, and then the gate of M5 is AC ground, because the gate of M5 is just the DC bias. So, this can be set to AC ground. The common mode signal at the gate of M1 and M2 for the time being, we are assuming it to be 0. There is no common mode signal applied. So, I can put this also to be AC ground. The gate of M3 and M4, however, is driven by my error amplifier. So, I will have the common mode output coming from the first stage, which is going to the error amplifier, whose output is basically controlling the gate of M3 and M4. So, this is the equivalent common mode half circuit, and you are having the Vref over here and the common mode signal coming from the main differential amplifier is fed to the positive terminal of the error amplifier. Now, in this case, we can assume the Vref to be my input port, and I can see that the final voltage that is fed back to the other terminal is at the opposite polarity. So, if I assume that the Vref is an input signal which I am willing to change to set up a new common mode voltage, we can see that the feedback voltage that is coming over here, that is at the opposite terminal. As a result, we can say that there is a series feedback at the input terminal of this amplifier. Whenever the feedback signal coming from the loop is at the opposite terminal of the differential amplifier, it basically effectively subtracts from the input signal. As a result, we can say that there is an effective negative feedback coming over here. And if I have to open the loop, I can break the loop over here at this point, and what we can see is that the output voltage over here is being applied as it is to the feedback terminal. As a result, what we can say is the Vf or the feedback signal is equal to Vo. So, basically the feedback factor is 1 essentially. So, the output signal after traversing the loop from the differential amplifier going into the fully differential amplifier common mode, the output common mode is applied as it is to the positive terminal. As a result, the beta factor is 1, and we are sensing the output potential of the output stage here. As a result, we are having a shunt connection at the output. So, once again series at the input, because we are subtracting the feedback voltage from the effective input voltage, and we are having a shunt connection at the output because we are having a feedback network beta equal to unity, and it is just passing the output voltage as it is to the non-inverting terminal of the amplifier. So, we can draw the transistor level implementation of this amplifier and then analyze this in the open loop case to obtain the stability, phase margin, etc., using the frequency response, and then look for the stability criteria where and how to add additional components in terms of capacitors to stabilize this circuit and obtain a reliable phase margin. So, let us look at that in the next module.